Assalamu alaikum. We are going to resume our lectures, and the next speaker is Professor Mouloud Nabil. He's from Khalifa University in the United Arab Emirates. Professor Nabil graduated with MS and PhD degree in medical physics from the University of Wisconsin-Madison in USA. He worked as a research assistant at the Biomedical Instrumentation Lab and research associate at the University of Wisconsin-Madison in Cardiovascular Research Lab. Professor Nabil published more than 55 journal papers and more than 75 conference papers. He earned 3 US patents in X-ray imaging development. His research interests are in medical physics and biomedical instrumentation in general, and in particular the optimization of medical imaging, the development of nanoparticles for X-ray and MRI imaging. He is an expert in his field. I'm very pleased to have him here with us for today, and he's going to share with us his thoughts about spectral CT imaging and AI-based material decomposition. You are very welcome.
Thank you very much. I would like to first thank the organizing committee members and the university management for giving us this opportunity. Now, this is the 3rd time I have the honor to come and participate. Okay, so without further ado, let me start. We are a group with Dr. Amr Raja. I will be presenting work of 2 students. One, Abdaraouf Bihoush, who is a PhD student with Dr. Hassan, and Noura Rahmani, who is a master student in medical physics from the UAE. So basically, I will be giving you a background about spectral imaging, mathematical background. I will not go too much in the math. Then I will speak about the master project for material identification and material decomposition work of Abdaraouf, and a conclusion. Okay. So Dr. Habib already introduced CT imaging, which is different from projection imaging. Basically, instead of taking projections of the anatomy on a plane, we construct cross-section images of the patient. And this is very important. The pixel values are usually Hounsfield units that are a function of the linear attenuation coefficient of the material. So here I'm showing the basic CT. So you have an X-ray tube, you have the patient, you have multiple detector array, and when the X-ray tube and the detectors rotate around the patient, we get projections. And using filtered back projection or iterative reconstruction, we can reconstruct the cross-section images of the patient, and each pixel either Hounsfield unit or attenuation coefficient. So just a reminder for the students, the X-ray attenuation coefficient, if you plot it versus energy, here we're showing, for example, for that of water in blue, bone in green, I think, and iodine. So you can see, for example, the iodine, there is a K-edge transition. That's why iodine is used often as a contrast agent in X-ray and CT imaging in general. So an important development was the dual energy CT. So this is basically imaging. There are different ways of achieving dual energy imaging, either switching the kilovoltage of the X-ray tube from low energy to high energy, and you can get, for example, a spectrum of low energy and collect an image, and when you change the kV, you get another image at higher energy. Another way is you having 2 X-ray tubes, and you have 2 sets of detectors at 90 degrees, and you collect images. Or you can also have detectors, 2 layers of detectors, where one layer acquires the low energy, and the layer behind it will acquire the high energy image. And using the 2 energy images, you can do very interesting things like material decomposition, getting virtual monoenergetic images. You can also get the atomic number, the electron density of the material. All of this was made by the development of dual energy imaging. The next major development in CT technology is the development of the photon counting detector. This was developed at CERN. This is the MEDIPIX detector. They are made, for example, of cadmium telluride, CZT, also cadmium zinc telluride, and some have developed also based on silicon. So this is a 14 millimeter by 14 millimeter array. It has about 128 by 128 pixels. The size for pixel is about 110 micrometers. So the important thing about these CZT detectors is the signal that they collect is unlike the conventional CT detectors that are basically scintillation detectors. The signal they collect does not differentiate in energy, or it's actually an integrated signal. So it's not separating the different energies. Unlike, for example, if you use sodium iodide or germanium detector, you can actually get spectrum, so you can determine number of photons that are emitted in different energies. The development of the MEDIPIX detector allowed us to do the basically energy discrimination. So the X-rays interact with the semiconductor, they generate electron and electron holes, and these charges are collected in the anodes and that are bonded to circuitry, and then you have the signal is actually proportional to the energy of the X-ray. So every photon that is detected by a certain pixel, the signal is proportional to the energy. So we have energy discrimination, and in the electronics we can put thresholds, and basically, so if you have this is, for example, the signal that is detected for every photon, and the height of the signal or the strength of the signal is proportional to the energy of the photon. So with the electronics, you can put different thresholds and detect only the photons that are above a certain threshold. So if you can have multiple detectors and you set different thresholds, and you only collect or count the photons that have a certain energy above that the threshold. This is a very important development, because now we have, in X-ray imaging, we have a detector that differentiates between the energy of the photons, and they can count the photons. And it's like we have, that's what we call spectral imaging. The most common name is used spectral photon counting CT, SPCCT. That's an abbreviation that I will be using in the rest of my presentation. So there are many advantages. There is, because you can set a threshold, you avoid the electronic noise. For example, you set your threshold above the electronic noise. We achieve a better spatial resolution than conventional CTs. As you have seen, the detectors are quite small, about 110 micrometers. They provide multiple energy detection, so you can have, from the same scan, you can generate images that correspond to different energy windows. Okay, we can exploit this for material differentiation, and that's what we will be speaking about today, is material decomposition that was done by two of the students. We can also reduce the dose. Spectral CT imaging allowed the physicists to obtain lower dose with higher image quality than conventional CTs. This is the Mars research CT scanner that we have in the lab. It's a company in New Zealand, and so they have the CZT, cadmium zinc telluride detector, and it's based on MEDIPIX chip, which is a CERN development. And so we basically, the field of view that we have, it's a small gantry, about 11 to 12 centimeter, and we have 5 energy thresholds. So we can, 4 energy thresholds, so we can get 5 energy windows. So when we scan a phantom or a small animal, we can generate from a single scan images for each plane or each cross-section. We can generate multiple images. Each image corresponds to a different energy range. So for example, if you take, this is a spectrum that was generated by software, SpecCalc, at 120 kV. We set the thresholds at 40, 50, 60, 60, 79, and we can get images corresponding to these different energy windows. So this is the image that corresponds to the photoelectric region from 0 to 40 kiloelectron volt. Here, this is the energy corresponding to the second energy window between 40 and 50, and so on. So these are, and you notice that the image that is in the photoelectric region has much higher contrast, because that's where we have large differences between the attenuation coefficient of different materials. So here, this phantom has different concentrations of iodine, of gold, water, and so on. So I think I have a... so this is, and obviously as you go higher to the Compton region, the contrast is smaller, because in the Compton region, the difference between the attenuation coefficients of the different materials becomes very small. It's almost independent on the atomic number of the material. Okay, so remember, from conventional CT, the Hounsfield unit is the attenuation coefficient of the material of that specific voxel minus that of water divided by the attenuation of water times 1,000. So for example, for water, we have a Hounsfield unit of 0. For air, it's minus 1,000, and so on. So this is the parameter, or let's, in our case, we just get directly the attenuation or the average attenuation coefficient that corresponds to the different energy windows. Okay? So if we go to dual energy CT, this is you have a spectrum at low energy, and you have a spectrum at high energy. And if you determine, if you expose the phantom or the animal or the human to that spectrum, you get an average attenuation coefficient. This is the formula of the average attenuation coefficient. So if, for example, in this case, let's say the minimum energy is 20 and the maximum energy is 80, you integrate and you multiply the attenuation coefficient, this from monoenergetic attenuation coefficient, times the spectrum, or the photon fluence versus energy, divided by the integral, the same integral over the photon spectrum. So this is an average attenuation coefficient for the low energy. And the same thing you get if you expose your patient to the higher energy, you get a second attenuation coefficient that corresponds to an average of the higher attenuation. So here, the only thing that changes in the equation, is the minimum energy is about the same. The maximum energy is now, instead of 80 kiloelectron volt, is in this case 140 kiloelectron volt. When we do spectral CT, we go, instead of only two energies, the detector, you use the single spectrum, it's one spectrum, but the detector has the ability to differentiate between different energy windows. So basically, we obtain for each energy window, we obtain the pixel value is the average attenuation coefficient for that. So we get, in our case, 5 images. Each pixel in each image will correspond to an energy window, and the attenuation coefficient is approximately, it's the same equation, except now the lower energy is this one. So for example, for this energy window, the lower energy is 60 kiloelectron volt, and delta E is 20 kiloelectron volt, and the same equation. So for each pixel in the image, we have 5 values, 5 pixel values, each one corresponding to different energy, and each one of these pixel values corresponds to an average attenuation coefficient. So now we have a lot of information. Basically, we have a spectral information, and we can exploit this spectral information to get information about the material, because the different materials have different attenuation coefficient. Okay, so I will be speaking about material decomposition and material identification. Material decomposition is basically separating and quantifying the different materials. So we assume each voxel in the object is composed of different material, and when we decompose, we generate the concentration for each of the materials. So we'll have an image of water, an image corresponding to iodine, an image corresponding whatever the material we choose to represent. Okay, so the output is proportional breakdown of materials within each voxel. And each material decomposition image is basically a map for the content of the pixels or the voxels of that material. However, material identification is just a classification problem. It's classifying each voxel of the CT image into one material class. So we have different materials, and we identify. This is water. This is iodine 6 milligrams per mil. This is iodine 8 milligrams per mil, and so on. So we will see how we can either do material decomposition or material identification. Okay, so we can write for if you have an incident X-ray intensity I0 and a detected intensity I, this is the equation that will, these are the attenuation coefficient, these are the concentration of the material in a voxel, and so you integrate for the number of materials that you have. So this is the exponential attenuation, it's exponential minus mu x, except now you have many materials in each voxel, and you have many voxels along the path of the X-ray. Now, if we assume that each voxel has different concentrations of the different materials, this is what we call Cm, is the component of each material at a certain location, and this is in 3 dimensions, x, y, and z. We can write that each signal, in this case, which is the attenuation coefficient, this is what we are showing as n, in ijk, it's because it's in 3 dimensions, can be obtained as the linear combination of the concentration of the material that is in that voxel times the attenuation coefficient of that material at that specific energy or energy window. So basically, we end up with a matrix equation where the S's are really the attenuation coefficients of the materials that we have in our image, and these are mu1 to mu_m are the attenuation coefficient of the different materials that we are using to decompose our image, and these are the concentrations for each material. C1 to Cm is a concentration for these materials. So we can use these matrix equation and solve them mathematically in order to obtain the concentration of each material in each voxel in our image. That's basically material decomposition. Okay, so if we let's simplify this. Let's write the attenuation coefficient of a certain voxel at a certain energy is just equal to the linear combination of AI times mu I, which is our AI is now the coefficient. Instead of the previous slide, it was Ci. Now we were calling it AI. You can basically write this matrix equation as this is the attenuation coefficient. These are the attenuation coefficients of the materials that we have chosen to decompose our images, and these are the parameters, the material decomposition parameters, or the coefficients of each material in that specific voxel. Okay, so you can invert this and you can solve. If you have only two energies, you have two equations with two unknowns, A1 and A2 are two unknowns. You can solve for A1 and A2. So this is what you can do in dual energy. When you go to multiple energy, now we have 5 equations, and with 5 unknowns, we can choose 5 materials to decompose, and so it becomes 5 equations with 5 unknowns, and we can also solve this using some different methods. So this is, I was not planning to show this slide. I was working with Doria on virtual monoenergetic images. Basically, you can think about this. If you have 2 materials, and it's like you have a vector, and you want to, in 2 dimensions, and you want to express this vector as a function of the vector in the x direction and the vector in the j direction. So that's 2 materials. So if you have a vector in 2 dimensions. If you have a vector in 3 dimensions, we can decompose it as the summation of, or a function of the x, y, and z unit vector. So it will be, so you can think about these materials as if they are vectors, and we are expressing any material as a function of these vectors. So this is here, I'm illustrating this. So you can write, let's say, for example, you have 5 materials. This becomes the attenuation coefficient. The A1 or alpha 1 to alpha n are the concentrations of each material that we have in that voxel. And so if you have five energy windows, you have 5 equations with 5 unknowns. Now you can add another equation. You can impose a constraint, and you say, if I add all the concentrations, they should be equal to 1. So that gives you an extra equation. So instead of, for example, if you have only 2 energies, if you add a third equation, which is that the sum of all the concentrations should be equal to 1, that gives you an extra equation. So you can use 2 energy windows in order to solve for 3 materials. Same thing, if you have 5 equations, 5 energy windows, if you add another extra equation of the sum of the coefficient has to be equal to 1, then you can solve for 6 materials. So this is the mathematical background. Obviously, we did the math, we did the mathematical construction, but our interest was mainly in applying machine learning, deep learning for material decomposition and construction. Okay, so first of all, let me go over the thesis of Noura Rahmani. This is material identification. So basically, she identified 22 materials: water, adipose, muscle, hydroxyapatite at different concentration to simulate bone, iodine at 7 different concentrations, gold 3 concentration, the phantom material, which is PMMA, air, and plastic vials, because we used some plastic vials for putting different concentration, and aluminum, which is the gantry material. Okay, so we use the QRM phantom, so you can, the phantom, you can put in it inserts that correspond to different materials, like for example, here is hydroxyapatite 400, we have here gold at 8 milligrams per mil, iodine at different concentration, but also we made plastic vials and we put different concentrations, for example, of gold nanoparticles, of other material that were not part of the QRM phantom, but we wanted to get information about that. Okay, so so these are the exposure parameters that we used. So these are, for example, here, this is an image of the phantom containing different materials, and you can see this is again a low energy image from 7 to 40 kV, and all the images that correspond to the different energies. Again, you can see here that we get the best contrast at the lower energy, between 7 to 40, which corresponds mainly to the photoelectric region. After we do ring artifact removal, the company provides a software that allows us to do this while preserving the attenuation coefficient, so we do not significantly affect the attenuation coefficient. And so we obtain these images. And then Noura, she used QPath and ImageJ in order to do the labeling, basically to select these different regions and to give them a label. So she constructed these masks using the basically manual procedure, but aided with the software. But once you do it for a slice, basically it's the same, because the phantom is aligned and we don't have to do much modification for labeling our image. So this is basically, it will constitute the ground truth for the learning. So these are ground truth images that are generated. So these are the 22 materials. She assigned for each material a certain pixel value. So these are ground truth images. So this is the different vials inside the phantom. These are the vials when they are protruding out of the phantom in air. So she used images inside the phantom and also in air. So basically, the process is collecting the spectral CT images, ring artifact removal, then manual attenuation of the masks, then we use the deep learning. So she chose NNUNet, which stands for non-UNet, indicating it refines and optimizes the existing UNet architecture. It's basically a utility that does a lot of the optimization internally. So some of the hyperparameters are changed inside this utility, and basically it optimizes the parameters, and then it gives you the final architecture that it has chosen as the optimal architecture for the NNUNet. So it has certain fixed parameters, certain rule-based parameters, and certain empirical parameters, but eventually you get the UNet architecture that is optimized for the different hyperparameters. So this is taken from the paper that was published about NNUNet, and you can see that, so these, here we have the fingerprinting for the data. So we input 5 images, each one of them correspond to a different energy window. Then these are the rule-based parameters. This is where it does most of the optimization for the different parameters. And here there are certain fixed parameters like the learning rate, the optimizer. There is internal data augmentation, and so on. So, but we can feed 2D or 3D images, and basically it's a UNet architecture. So this is the, after she has been working, this is the architecture, the topology of the UNet, okay? So as you can see, I think there are nine stages here. This is the compressive path, and this is the expanding path of her pipeline. And again, the original images were 1280 by 1280. Each pixel is about 0.1 millimeter, and the patch size is the batch size is 2. Patch size 1280 of 1000 by 1024. So it's a UNet optimized topology. These are some other parameters. The filter sizes, for example, the number of encoder-decoder stages are 9. Okay, and so if you need more details, we can. Obviously, she looked at the cost functions or the loss function during the training and during the validation. So the blue one is the loss during the training. The validation is in red. She also looked at the dice index and the moving average for the dice index as the model is being refined. She used Colab Pro with the V100 GPU and 5-fold cross-validation scheme, and each of the folds took 6 hours, so it took about 30 hours, and eventually we obtained. So for example, the mean dice for the 5 folds is shown here, different values from 0.86 to 0.71. It's not really a big variation, and so this is the results. So here you have a deep learning. First of all, this is the ground truth, and the color is color-coded for the different materials. So here is the color code. For example, this dark green is hydroxyapatite 800 concentration. The red is muscle, and so on. So these are the different materials. This is the deep learning prediction, and as you can see, the deep learning, you can see we have a good identification except some materials. For example, here, the middle one, we have muscle, but some of the muscle was identified as blue, which is water, I think. Yes, CT water. So the materials that have close attenuation coefficient, or their attenuation coefficient is very close, and when you look at the distribution, are not easy to separate. So the model identification gets confused sometimes. Also, notice that the edges of the materials, we have some mismatch. That's the white pixels, because when she was doing the manual outlining, she cannot do it perfectly, obviously, so she would miss certain pixel value. And that's why at the edges of the different materials, we have some missed identification or mismatch between the ground truth and the deep learning prediction. So these are other images and others. So sometimes we get, so for example, I don't know what happened here. Clearly, we have more misidentification in this slice or in this image. But in most cases, we had very good results, except for the materials that have very close attenuation coefficient. Okay, so these are the different parameters. So the average dice was 0.797. You have the accuracy, specificity, the recall, and the Jacquard index and precision. So these are some of the metrics that she used for evaluating the performance of her model. So this is in a graphical form. We have here the different parameters, dice in red, the Jacquard index in blue, pink, and sensitivity, and so on. And you can see, usually for example, gold concentration, the higher concentration, we usually achieve much better results than the lower concentration, because at the lower concentration, they become overlapping with some other materials. Same thing for iodine. So iodine at low concentration, the performance is not so big, but at higher concentration, we get very good identification. Same thing for hydroxyapatite, and these are the other materials. Okay, so this explains why some materials are quite difficult to compare. So if you look, for example, at muscle and water, muscle is in yellow in this case, and you have water, CT water is in blue, and as you can see, the average value and the standard deviation, there is a lot of overlap. So for example, here, this is in the 4th energy window, and you can see that they are very close. This is the first energy window, which is from 7 to 40 kiloelectron volt, and you can see the average values. If you plot the distribution, the average values are very close, and the standard deviation, they overlap. That's why we have mixing and identifying these materials that are very close. Okay, so I asked her to compare with the material decomposition. This is the Mars. They provide their own material decomposition, which is based on mathematical method, but it's material decomposition. So she had to convert material decomposition into identification by selecting, we struggled to find a way of determining thresholds. And basically, so originally, it generates these images. So this is hydroxyapatite. This is the map for hydroxyapatite. Adipose, this is a map for water. The map for gold, muscle, and iodine. Then she had to convert this into identification, and obviously, so this is one of the comparisons. So this is the original distribution of the different materials. This is the original image after ring artifact removal, and then this is the ground truth, and this is the material decomposition done by the Mars mathematical software, converted to material identification, and this is her developed model. So you can see that there is noisy images because the different materials are mixed, while in material identification we have sometimes some confusion, but usually it's between materials that have very close distribution. So these are comparisons between for the dice and the sensitivity between her developed material identification based on NUNet and the material identification from the Mars MD software, and you can see, in my opinion, it was not a very fair comparison, but we end up with much better metrics or results than material decomposition. So I asked her, maybe it's dependent on the geometry. We have circles and so on. Can we test this on an actual tissue? So here, this is a steak that Abdarov obtained from a butcher, and he put some iodine concentrations, and we collected CT images. And so this is, you can see it contains muscle, contains fat, bone, and different iodine concentration. This is the CT image, and this is the material identification image that was obtained using the NUNet, okay? And so this is, for example, a region of fat here. Okay, these are the different iodine concentration, and that's why you see the purple color. This is the material decomposition obtained from the Mars MD software. It's material actually decomposition converted to identification, and obviously you can see there is quite a difference in. Okay, so obviously there are limitations to the study. Let me go to the study for the material decomposition that Abdarov did. Okay, Abdarov came up with a very interesting technique. We wanted to avoid labeling and so on. So what we did, we generated synthetic images. And the way we did it, so we take a CT image, for example, and then we, obviously he did this all by the Python software. If you select a region, you get a histogram, or the distribution of the attenuation coefficient, the number of pixels that have a certain attenuation coefficient. Using this distribution, he basically generated synthetic images. For example, here, this is an image that corresponds to 4 different materials. So the pixel values are generated by sampling the distribution of the material that we obtained experimentally. So this is what we call inverse transform sampling. Is basically getting the distribution, using this distribution to generate synthetic images, and we can play with the shape, and we can use any shape so that the model is not shape dependent, okay? So this is a very nice method, and since he generated the images, he did not need to generate a ground truth, because he already knows, or the software, what material is generated here. So basically, the ground truth is already there, and he used, I think, 32,000 for the training images, and he used the synthetic images to train the model. And he used synthetic images for validation of the model, and he used real images in order to test the model performance. Okay, so again, this illustrates the problem when you have materials that have very close distribution. So here we have gold in yellow and gadolinium in orange, I think. And so these are the different energies, different energy windows, and you can see there is a big overlap. So if you look at, for example, lipid and water at a certain energy, basically you cannot separate them, because visually you cannot separate them, and even when you look at their distribution, there is a big overlap. This is the pipeline he used. So this explains, so he used the phantom, material phantom, and he also used the stake with the different iodine concentration. He scanned these, he obtained the distribution, and from the distribution of the materials, the phantom materials, not the stake, he generated the synthetic images, and he used the synthetic images to train the model. And the model is based on UNet, but with different variations. And so he knows he has already the ground truth, so he can check the performance of the model. So it's the innovative part is really the generating of the synthetic images. He was able to use a very large number of images. Deep learning needs large databases. So he basically used three variants. He used he called it inverse sampling material decomposition net, ISMD net, which is based on UNet structure. He used in the compressive path, he used dual resident blocks from ResNet. The filters, I will show you in the 16, 32, and 64 filters. Then what he did, the second variant is he added the attention mechanism. So he added the channel attention mechanism. And also in the third variant, he included a transformer in the bottleneck of the UNet. So these are, so here, this is the encoder path of the UNet, and this is the decoder path, okay? Now, basically, originally he did not use the channel attention mechanism, so the path was just like this. Okay, then he added the channel attention mechanism, so this is the second variant. And the third variant, he added the four-layer transformer in the bottleneck of the UNet architecture. So we feed in the images, and we generate the material decomposition images for the different materials. Okay, so let me go to the so here. So he used 32,000 for training, 10,000 for validation. He used the Adam optimizer, and basically the goal is to reduce categorical cross entropy. And the metrics he used the root mean square, the precision, F1 score. I think he also used the peak signal to noise ratio. Okay, so this is the result of the phantom. So this is a phantom that has different material, including water, gold at different concentrations, 2, 4, and 8. We have different concentration of iodine, 4, 8, and 16. We have different concentration of gadolinium. We have calcium, 3 concentration of calcium. And this is the phantom material. So the images that were generated, he generated for different, this is his UNet basic structure. This is InceptNet, is another deep learning that we also implemented from the literature. This is the basic UNet. This is the Mars material decomposition, which is a mathematical, and these are 2 other mathematical methods, direct inversion, and this is another one. So basically, he compared his results with 2 other deep learning topologies, and also with 3 different mathematical material decomposition methods. The first row shows, for example, the gold. You can see the gold here. These are the gold tubes. So you can see this is the ground truth. The first column is the ground truth. This is the ISMD net, and these are the other nets. And you can see that the ISMD net has better than identification, for example, of gold than the others. Let's look at, for example, gadolinium. Gadolinium is here. So you have 2, 4, and 8 milligrams per mil, and this is the ground truth. This is the ISMD net, which is the basic UNet, and this is 2 other deep learning method. This is the Mars MD, and other three mathematical methods. Okay, iodine, same thing. So overall, we let's see. This is the root mean square for the different methods. So we have about 8 methods. And so for calcium, for example, you can see that the 3 variants, the ISMD net with attention and with the transformer, we obtain much lower root mean square error than the other methods for calcium. Same thing for gadolinium. Same thing for gold. Okay, iodine it outperforms the other methods. In terms of lipid and water images, there was no big difference. So this is one of the things that we struggled with, is that we could not achieve, obviously, lipid and water, they are very overlapping attenuation coefficients, and all of the methods did not achieve very good results. This is the F1 score and the precision. The blue one is the ISMD-Net, and the other colors are UNet, INSEPT-Net, the Mars-MD, and the other two mathematical methods. And you can see the F1 score at the different concentration is higher for gold. The blue color is the ISMD-Net, is better for gadolinium, calcium, iodine. Okay, so it looks like the other materials are covered. Oh, sorry, it's the precision. So this precision also, the blue color is a precision. And again, you can see that for at least these materials, gold, gadolinium, calcium, and iodine, we achieve better performance than the other methods. Okay, same thing, he did the image of the steak, and he did the material decomposition. So this is ISMD-Net with attention mechanism. This is with a transformer, INSEPT-Net, and UNet. So all of them are deep learning methods. These are the three variants that he implemented. And this is a muscle map or muscle material decomposition image. This is the bone, and so the bone is here, okay, and you can see. So all of them, basically in the bone, they had good results. This is iodine, okay, and you can see that there is some confusion of iodine. For example, I think the tissue that is next to the bone is sometimes the material decomposition gives us high concentration of iodine in the vicinity of bone. But these three methods outperformed the INSEPT-Net, and the UNet is actually comparable. This is the lipid or the fat map, and you can see that the three variants that he used almost have the same performance. In fact, if you look at this table, this gives the comparison of the different methods, including the two deep learning methods that we used, adopted from the literature, and the three mathematical material decomposition methods. And you can see for iodine, gold, gadolinium, and calcium, this is, I forgot, yeah, this is the precision. You can see that precision is the highest for the three variants, but it's not consistent. For example, ISMD-Net performed higher for iodine and gold, while the ISMD-Net with the transformer was better for gadolinium, and so on. So I asked him to generate these color images. This is the direct inversion. This is Mars-MD. These are two mathematical methods. This is his ISMD-Net, and as you can see, the red is for used for the muscle. I think the white is used for bone, and the creme color is used for fat, and his result is much better than the mathematical methods. Okay, so where is this leading us? We basically want to generate images. This is work done by other groups. So you can see that material decomposition, now you can generate an iodine map and a barium map, so two contrast agents injected in the animal at the same time, and you can generate these color images. This is another study for composition or material decomposition for bone. So we can decompose in terms of calcium, iodine, and water content of the bone, and you can basically generate these very nice color images that gives us the concentration of these different materials in the bone structure. So this is important very clinically, and you can also compare to the histology results. So you can also take a tissue sample and image it and do material decomposition or material identification. We are planning to build a system, a new system using spectral CT for the purpose of tissue characterization. So in the end, so for example, this is a very nice video. You can see this is the picture of the artery that was removed, and when you generate images, you can look where the lipid is, the calcification, the soft tissue, and this is very nice high-resolution images. You can generate these videos. Okay, so the past Röntgen, he took the X-ray image of his wife, and this is how it looked. Presently, we have much better images with high resolution and high contrast. Most of the doctors are still using grayscale images. A lot of development is being done but still the diagnosis is still being done on grayscale images. Basically, the medical doctors are not using the full spectrum of the human eye, because we see in color and we enjoy much better when we see a movie in color than seeing it in black and white. Okay, so we are only using part of the ability of the, and this is where we expect the future will be. So we will be generating color images, not only for material decomposition. Dr. Habib spoke about parametric imaging. The parametric imaging is now going to become possible in spectral CT images. So we will be able to generate virtual monoenergetic images, material decomposition image, effective atomic number images, electron density images, and so on. So these parametric images are going, we hope that they will enhance the diagnostic capability of the medical doctors. So this work, I'd like to acknowledge Dr. Amr is, and myself, we are working together. We have a number of students, Bria, Abdul Raouf, Noura Rahmani, Yusuf, Mohammed Zabi, and Hibas.
Yes, you did. Thank you very much for this wealthy presentation.